Oh, thank you very much for correcting because I am talking, but the mic was muted. Okay, really sorry for that. Okay, so let me repeat. As I was saying, so today we're going to talk about complex frequency. And when we talk about complex frequency, we're going to talk about S as the representative of complex frequency. So when we talk about frequency, we essentially usually we talk about positive real numbers as frequencies, representative of frequencies. And in this one, we are going to talk about positive frequencies, negative frequencies, and also the further generalization, that is the complex frequency. Okay, so again, in general, frequencies can be represented using a complex number. Okay, and in this one we are going to introduce the term conjugate variable. Okay, so we shall represent that frequency is a conjugate variable of time, which is time, and we're going to talk about some generalization of that idea. Okay, and then we're going to talk about a specific type of complex plane which is known as the S plane, which is very essential, very crucial in the discussion of control systems. And then lastly, we're going to end with a discussion, with a full-length discussion on stability. I don't know how far I will be able to discuss on Bibo stability, but we will have a discussion on Bibo stability nonetheless. Okay, and if I cannot complete the discussion on Bibo stability in this class, then we shall continue that in the next one. Okay, so nonetheless, we're going to talk about complex frequency and what that term actually is. Okay, actually means. All right, so let's start. Okay. So we are familiar with Laplace transform as well as Fourier transform. So we know that Fourier transform in general tells us about the composition of a signal, right? So if a signal is, of course, if a signal is representable as a sum of sinusoids of different frequencies, then the Fourier transform in general can give us the constituent components, can tell us about what components, what different sinusoids actually make up that particular signal. Okay. And in general, for many signals, this kind of approach is not applicable. There are many signals which cannot be represented in general as a sum of sinusoids. Okay, for that reason, we have Laplace transform. Laplace transform essentially multiplies the decaying factor with the signal so that the signal actually, the integral actually converges, which means that we do represent the sinusoids, but in a the sinusoids are decaying in this regard. Okay. So let me just again write down the very definitions of Fourier transform and Laplace transform. Let's say xt is a signal, then this integration, sorry, rather this multiplication actually multiplies a signal with the sinusoid of the frequency omega. And of course, if we integrate this, we actually did this derivation properly in our signals and systems classes. If we do this integration, what we are essentially looking for, we are looking for the magnitude, sort of magnitude of the omega radian per second component present in this signal. Okay, and just like that, so we shall vary the value of omega. So essentially this becomes a function of omega. So after calculating this function, if we are trying to look for the magnitude of the component that has a frequency of a certain frequency of, say, for example, 1 radian per second, we would just put omega equal to 1 in the final result that we obtain, and that way we can actually obtain the magnitudes, relative magnitudes of the constituent components in a signal. So this is Fourier transform. Okay, and similarly, as you already know, that there are many signals for which the Fourier transform in the conventional sense does not exist, which means we are in the conventional sense we cannot represent the signal as a sum of sinusoids. So for those situations, we actually multiply the signal with a decaying factor, with a real decaying factor. So keep in mind that this is not a decaying factor, this is a sinusoidal representation. This is just a sinusoid. But for Laplace transform, we do the same Fourier transform, but instead of calculating the Fourier transform like that, we multiply xt with a factor that ensures that this signal xt decays, which means that we are ensuring convergence. Okay, and then we actually calculate the Fourier transform. So that is how we define Laplace transform. Okay, so of course we combine these two, and when we combine these two, we have something like we get something like xt e to the power minus sigma plus j omega t dt, and we eventually call this sigma plus j omega t as xs. Okay, sorry, as s. So essentially we have this integration. Okay, So that is what we call the Laplace transform. We express that as S. So where we are defining that S is nothing but a specialized version of that. So essentially S is sigma plus j omega. So that is the representation we regularly use. Alright. So that's what we call the complex frequency. So this S term is actually known as the complex frequency. Now let's have a small discussion on frequency in general. Okay. So of course, frequency is how frequent. The name frequency tells us how frequent something is. Okay. So for example, if we say, okay, this signal has this much frequency, which means that this signal repeats with a certain periodicity, which means, let me tell you, for example, if I say a signal has a frequency of 1 hertz, that means the signal repeats itself after every 1 second. Just like that, if a signal has a frequency of 2 hertz, the signal repeats itself twice every second. Just like that. Okay. And similarly, frequency is inherently related to rotation. So 1 hertz is sort of can be assumed to be 1 full rotation. Okay. And in a second, and that is like covering a 2 pi angle in a second. So that is 2 pi radian. Okay. So instead of saying 1 hertz, we often mention 2 pi radian per second. It means the same thing. Okay. So that's the same thing essentially. So we know how to represent frequency. We essentially know everything that there is to know about omega. Okay. But let's talk about frequency in general, and let's talk about how we can actually describe all these things properly. For example, let me just ask you a very simple thing. What do you think of negative frequencies? If somebody asks you, are there negative frequencies, or are frequencies just positive quantities? The answer is obviously yes, there are negative frequencies. And negative frequencies, if we think about a frequency as a representation of rotation, then obviously negative frequency is the representation of that same rotation in the opposite direction, right? So if I say something is rotating at 10 radian per second, okay, and at the same time I say something else is rotating at minus 10 radian per second, then obviously based on how we measure angle in trigonometry, okay, we can say that the rotations are essentially in the opposite direction. They have the same magnitude of revolutions per second, okay, same magnitude, same speed per se, okay, but when we talk about rotational velocity, so that indicates an opposite direction essentially. Okay, so it is rotating in the opposite direction. So negative frequencies essentially represent rotations in the opposite direction. Okay, so if you have a conventional direction, then that you consider to be the positive direction, and then negative frequency would actually represent the rotation in the opposite direction. So that is something easily understandable. Okay, so omega is not restricted to positive quantities, but it can also be negative real numbers. Okay, and omega can be 0. Of course, omega 0 means that this signal is constant. Essentially, it does not have any frequency term associated with this. Okay, omega is 0 means the signal is constant, which we often call it a DC signal. But don't what should I say? Don't confuse omega equal to 0 with omega tending to 0. Okay, just keep in mind that when we say omega equal to 0, we mean it's a DC signal. Okay, it's a DC signal, so which is a constant signal. So when we mention omega is equal to 0, we of course we're talking about something that is not changing with respect to time, so it has 0 frequency per se. But when we mention something like this, omega is a very small quantity, omega tending to 0, not exactly 0. That means, in other words, the time period of the signal, which is 2 pi by omega, we are of course using radian per second as the unit, 2 pi by omega, so that would actually tend to infinity. Okay, so this indicates that the signal is aperiodic. So there is a very stark distinction here. Okay, so if omega is really small, infinitesimally small, extremely small, that indicates the signal we are talking about is aperiodic. Okay, but if omega is equal to 0, then that's a constant signal. So DC signal or a constant signal. Okay, there is a very stark distinction here. Okay, so very small and equal to 0, they are not the same thing as far as the frequencies are concerned. Okay, so again, let me repeat, 0 frequency means it's a constant signal or DC signal, but low frequency, very low frequency actually indicates that it has extremely high time period, and so high in fact we have an infinite amount of time. We have to wait an infinite amount of time for the signal to repeat. So that is kind of the definition of the period of an aperiodic signal. For an aperiodic signal, we assume the period to be infinity. And just like that, we actually derive this sort of expressions, like in Fourier series, we have an expression like this. Then we actually extend the Fourier series for aperiodic signals with the approximation that the time period is extremely large, and thus the frequency is extremely small. Fundamental frequency is extremely small. Okay, fundamental frequency, of course. So that is something we, of course, have complete rigorous ideas about. Okay, all right. But let's look at this expression here. Look at this sort of expressions. In these sort of expressions, we see something very important. Okay, that on top of E, we have certain things. Okay, let's say we have e to the power j omega t, or something like e to the power st. Okay, we definitely know that t is representing time, so t is definitely time, and it is measured in seconds. Okay, that's just time, for example, this one. Okay, but try to understand one thing. So since seconds is a dimension, quantity with a dimension, okay, it is not a dimensionless quantity, which means try to understand, say if I write t, e to the power t, okay, e to the power t, without any regard for any dimension, then there is a small problem. Okay, if t is, for example, 2 seconds, let's say, for example, if t is 2 seconds, okay, if t is 2 seconds, and I just mentioned xt is equal to e to the power t, then let me ask you this very thing. Try to understand. There is a problem with this sort of what should I say, expression. So if I now say, what is the value of x2? What I'm asking you actually, what is the value of xt when t is equal to 2 seconds? So let me just write it down. x2 is actually xt at t equal to 2 seconds. Notice that there is a unit here. There's a specific unit here. Okay, so that would actually indicate that I'm looking for e to the power 2 second. Obviously, the units needs to be taken care of, right? So just like that. So for example, I multiply 2 second with 3 second, I actually get 6 seconds square, right? So units also have to be algebraically manipulated just like that. So because of this very reason, this is actually e to the power e square, then e to the power second. The unit becomes something absurd like that. Try to understand something very important here. Okay, the unit becomes something absurd like that. Okay, so is it understood? So we have to think about this very importantly. So there is an absurdity in the unit here. Okay, the moment we say something like that. So inherently, when we actually do this sort of calculations, we inherently get kind of skip the second, right? We inherently kind of skip the second, right? That's obvious. I mean, this is not unobvious. I mean, this is quite obvious. We skip the second so that the this sort of problem with units do not happen. Okay. But where did that go actually really? Okay, I cannot just get rid of the second just like that. Okay, I cannot just get rid of the second just like that. We inherently assume something very crucial here. We inherently assume that there is something multiplied on here. Okay, say for example, whenever I'm saying a signal is represented as e to the power t, where t is seconds, t is in terms of seconds, we inherently assume something actually. We assume something like there is a factor that is actually multiplied here with t. We inherently assume that there is a factor that is multiplied with t, and this factor a is not a unitless quantity. This factor a is not a unitless quantity. Instead, what we assume in our mind, okay, based on the particular context, that a is actually a unity quantity, okay, but it has a unit of that is the reciprocal of this quantity. So for example, if t is in terms of second, then that would be per second. So this is something we assume inherently, but we never talk about this really. Okay, we say that now you see this is perfectly fine. Do you understand what I mean to discuss here? Okay, whenever we say e to the power, let's say xt is equal to e to the power t, there is a big problem. We cannot put t seconds on top of exponentials because the unit will also get messed up accordingly. Okay, so when we do some manipulation on a physical quantity, so t, time is a physical quantity, so the units must be manipulated accordingly, right? Units must be manipulated accordingly. So we know all these things from our school level classes, right? So what we essentially do, we actually assume that there is a quantity multiplied here and that has a unit which is reciprocal to this. So which actually takes care of this quantity, so that on top of this I don't have anything that has a unit and that messes up everything. Okay, so that is quite obvious, I believe. So this is not a very difficult thing to understand, I hope. Okay, so this is something we actually do without telling anybody, without even telling ourselves. Okay, so this is something we never put any thinking behind, right? But we actually do these things automatically. Just like, let's take another example, a very common example. Let's say xt is equal to sine t. Now I'm asking you to calculate x at 2 seconds once again. Okay, x at 2 seconds. So what I'm asking you once again is to calculate xt when t is actually 2 second. Okay, 2 second. But do you write something like this, sine of 2 second? Because if you did, then you have a complete mess. Because you don't know how to calculate sine of 2 second. You know how to calculate sine of 2 radian. Okay. You don't know how to calculate sine of 2 seconds, but you know how to calculate sine of 2 radian. Okay, 2 degrees, for example. Okay, if you are weird. Okay, you know how to calculate sine of 2 radian, but not sine of 2 seconds. Okay, you understand what I'm saying? So what you, again, once again, inherently assume that this quantity is not just sine t. This quantity is actually sine omega t. You inherently assume that. Try to understand something. We inherently assume that this is not just sine t. This is sine omega t. Okay, and this omega in this example is 1, but not just 1, it is 1 radian per second. Now, of course, radian is unitless, so at the very least, it must be 1 by second. A unit that is reciprocal to this quantity, this quantity with unit. Okay, so now with that being said, if I assume that, then of course I don't have any problem in the calculation. But now this unit is now gotten rid of. Okay, the moment I put that, because since this is omega t actually, and omega actually has a unit which is reciprocal to this, now we have gotten rid of that second here. Okay, do you understand what I'm saying? So we actually have gotten rid of that. So that way we actually can calculate something like sine 1, so that has a unit of second, and then we have calculated 2 seconds. So that actually does not cause any problem. Okay, and of course radian is a dimensionless quantity because radian is a ratio of two quantities, arc length divided by radius, right? So radian is a dimensionless quantity, and for many situations, to comply with some other calculations, we use radian per second as the unit of frequency, as a reciprocal variable. So what I say is that we do not think about them, but they are there. These variables which make sure that we have a unitless quantity or rather dimensionless quantity inside these variables are called conjugate variables. These conjugate variables exist all the time. These conjugate variables do exist all the time, but we do not really think about them as much, if I say so. Okay, but they do exist all the time. Okay, so I think this idea clears up everything. So this is what we mention as what we call the conjugate variable. Okay, so conjugate variables, once again, take care of the units. Okay, so that we put a dimensionless quantity, because sine theta, we say sine x or sine theta, this thing must be dimensionless. This thing, whatever we write here, must be dimensionless. I do not say unitless, I mean dimensionless. Okay, you understand the difference between unitless and dimensionless. Okay, so for example, radian is a unit, but it has 0 dimension. Okay, it has 0 dimension because radian is essentially arc length divided by radius. So it's essentially like meter by meter. So it is dimensionless. Okay, so this quantity must be dimensionless. Okay, this quantity must be dimensionless unless we are adding or multiplying things. And when we're adding things, we also have to think about dimensionality. Like we cannot add 1 meter with one what should I say, with 1 Kelvin, say, or let's say 1 degree centigrade. We cannot add them, right? So they are dimensionally different quantities. Okay, so that cannot be added, of course, because they have to match the dimensions. Okay, for multiplication it's not a problem, the units also get multiplied. For division also, that's not a problem, the units get divided. For subtraction, the units must be same, so the dimensions must be same at least. And for these functions, essentially they take on only dimensionless quantities. Like radian is a dimensionless quantity, that's fine. So when I say sine x and x is, for example, in meter, okay, we are inherently assuming that there is a quantity inside this, okay, that is getting multiplied with this to make sure that the whole thing becomes dimensionless. Just like that. Okay. Physicists who study quantum mechanics, so we understand that why omega is the frequency. Why does omega have to be a frequency? Because it is appearing. Just hold on for a second. Right. So as we see, all right. So as we see that this term actually, this omega actually appears on top of exponential. So obviously this has to be a conjugate variable to t. So we see that when I'm writing v to e to the power j omega t, of course j is dimensionless, so nothing to worry about that. So this is like e to the power j theta. This theta has to be a dimensionless quantity, which means it could at most be something like radian. Okay, let me increase the number of pages here. Okay, this theta must be a dimensionless quantity, and at most it could be something like radian. So obviously, since this has to be a dimensionless quantity, whatever the unit of t is, the unit of omega has to be a conjugate of that. Okay, unit of omega has to be a conjugate of that. Once again, let me repeat, even if I write e to the power t, we are inherently assuming that there is an omega here, and that omega has just the opposite unit of, reciprocal unit of this t, so that this function actually gets a dimensionless quantity on top of it. Okay, so e actually gets a dimensionless quantity, otherwise we are going to mess up the units. So obviously this omega, the unit of omega, so this is with third brackets, with this square brackets, we actually represent the dimension of a quantity. This omega must be dimensionally reciprocal to that of time. Okay, this omega must be dimensionally reciprocal to that of time. So this is something we call the conjugate variable. Okay, and now what is the reciprocal of time? Of course, frequency. That's why we say that this omega quantity is a frequency. So this is, if this is time, then this omega has to be something called frequency. Okay, frequency. Of course, frequency, as long as it has a dimension of 1 by second, it's fine. Okay, for example, if I represent omega as radian per second, of course the dimension itself is 1 by second, because radian has 0 dimension, it's meter by meter. Okay, so the dimension itself is 1 by second, so not a problem there. Okay, so that's fine. So again, so that's a conjugate variable. Okay, so we are discussing conjugate variables. And now to understand this a bit further, let me tell you that this sort of conjugate variables do not just exist in as time and frequency. They exist in other domains as well. For example, those who study physics, okay, those who study physics and especially quantum mechanics, they write a very similar expression. They write a very similar expression, and where the position of a particle is represented with x, and the normalized momentum of a particle is represented with p. Okay, momentum of a particle is represented with p, and the function is often represented. So they use a different notation for Fourier transform. Let me use that particular notation here. Of course, we talked about this different types of notations for Fourier transform. I mean, how to actually take care of these things. We talked about in our classes, but don't worry about this. You see, now in quantum mechanics, we are talking about the momentum and instantaneous position of a particle. Okay, momentum and instantaneous position of a particle. And you obviously understand that since these two are appearing here together, like on top of E, they must be conjugate variables. This momentum and instantaneous position, they are conjugate variables. Okay, so we are saying that x, which is the position of a particle, and p, which is the momentum of a particle. Okay, a normalized momentum, I mean. Of course, momentum divided by Planck's constant, etc. In quantum mechanics, of course, a normalized. Okay, so when it's position and momentum, so they are conjugate variables. So you can see, of course, from this you can understand that if the position is measured in terms of meters, then normalized momentum is of course being measured in terms of the unit 1 by meter. It's supposed to have a unit which is 1 by meter, okay, per meter, something like that. Okay, that's normalized momentum once again. So that is something that people studying quantum mechanics they use. People studying particle physics they actually use this kind of sort of Fourier transform. They are represented like that. Now you have, of course, even if you have studied a little bit of quantum mechanics, of course you did some part of that in your school as well as in your primary years in your college. You have studied some bit of quantum mechanics at least. You definitely have heard of Heisenberg's uncertainty principle, right? You have definitely heard about Heisenberg's uncertainty principle. And of course, instead of asking you, let me just kind of paraphrase this in a simple fashion. The idea is that if you have a very small particle, like a quantum particle, you can, if you precisely know its momentum, okay, if you precisely know its momentum, you cannot precisely know its position. And just like that, if you precisely know the position of a quantum particle, then you cannot precisely measure its momentum. Okay, so if you can precisely locate or precisely know the position of a quantum particle, then you cannot precisely know the momentum. Or similarly, if you cannot precisely if you can precisely measure the momentum, you cannot precisely know the position. Now, what do I mean by precisely knowing something? Okay, what is precision? Precision is something I say, for example, after an exam, if somebody asks me, maybe my classmate asks me, how much are you going to get in this exam? Okay, if I say, okay, I'm going to get 90 exactly in this exam, that's called precision. Okay, now I'm less precise if I say, okay, I'm going to get somewhere between 80 and 90, then I'm slightly less precise because I'm giving a range, okay, range of values with which I can get the marks out of 100, maybe something like that. Okay, so if somebody else in another exam, somebody asks me, okay, how much are you going to get in this exam? I'm gonna say, okay, maybe from 70 to 90, something like that. I'm even less precise now. Okay, got it? So this is what we mean by saying precisely knowing something. Precisely knowing something means, so just like, you know, the exams, if you get a grade 10 grade, okay, you're not sure that you actually got 100 out of 100. You could have gotten something between 90 and 100, right? You could have gotten 91, that still would have given you a 10 grade. Okay, you could have received 95, that still would have given you that same 10 grade. So this is kind of an imprecise way of measurement. Yes, it is. So somebody asking, isn't it important that we actually ensure that this is radian here? Yes, that's absolutely important, because the thing is, this radian is so inherently, what should I say, intertwined in these calculations. So that's why the radian per second is the unit of the reciprocal variable. Okay, the radian is the point being, if I just say calculate sine 2, what is the unit of 2 you assume? Do I have to say sine of 2 radian? No, by default it is assumed to be in radians, and that's how so important this is. Okay, even if we don't mention it, it is there. Okay, it is there. Okay, so omega could have a unit of, just keep in mind, omega could have a unit of 1 by second. Not a problem. Not a problem at all. Okay, because whatever quantity goes inside that, as long as it is dimensionless, it's fine, and it is assumed to be in radians. Not a problem. Okay. All right. So with that being said, I think I cleared up your confusion. Okay. So what I mean is that by saying that something is imprecise, I mean I know it with a certain range. I know it with a certain range. Okay. That, okay, it is within this range, and that is what quantum mechanics is really. For example, you have probably seen this sort of pictures. Now, why am I telling you all this? Is it somehow related to electrical engineering? Yes, you shall know shortly. For example, you all have seen this sort of pictures of atoms. When you were small children, so there was protons, so etc., neutrons, etc., inside this nucleus, and there would be electrons running around like that. Okay, electrons running around like that in orbitals. Now that's the picture of an atom you see. Unfortunately, so later on you saw that, okay, these were some sort of pictures for atoms, like electrons are traveling like that. You have seen these sort of pictures. Okay, this sort of pictures. But this is absolutely terribly wrong. I really feel sad when I see these sort of pictures. Atoms do not look like that. Atoms do not look like that. These orbitals are not like that. Okay, not precise paths like the orbitals of the planets. So this is kind of planetary representation. So this is not like the star, and these are not like planets. Okay, for quantum mechanics, the thing is these particles. Okay, if we knew the momentum of these particles, then we would only know. Hold on. Yes, it is a cloud-like structure. What I mean by a cloud-like structure. So when I talk about an electron in a certain orbital, we kind of know its energy. Okay, energy, how much energy it could have. So we kind of more or less precisely know how much momentum it could have. And if we precisely know how much momentum it could have, then we can only say, okay, these are the rough locations in which it can, the electron can be. So that's how electrons look very weird. Let me just show you a YouTube video, and that's a really fantastic channel. I like it. It's called Minute Physics. Okay. Let me just show you, not a video, just I'm going to show you just a tab from that. You can actually watch this video. Okay, so that's a video from Minute Physics, the channel Minute Physics. Fantastic channel. You might want to subscribe into that. So this is sort of how this is sort of how an atom actually really looks like. Okay, so you see the position of the electron is essentially, position of the electrons are essentially a probabilistic quantity. We can say, okay, these are possible positions. Okay, so if we know the momentum precisely, we can only talk about the position roughly. Okay, similarly, if we know the position precisely, then we can talk about the momentum roughly. Okay, so that's how an atom really looks like. Okay, this is a fantastic channel. I would suggest you subscribe to this one. Okay, this is Minute Physics. Okay, all right. So with that being said, so what we are saying that this is not true. That's what I try to understand. This is not just true for quantum mechanics. This is just not just true for quantum mechanics. This is true. Mark my words. Remember this. This is true for every set of conjugate variables. In real life, wherever we encounter conjugate variables, this is true for every set of them. Okay. Wherever in real life we encounter conjugate variables, this principle of uncertainty is actually valid for every set of conjugate variables. And when I realized this back in like 2016, this was a big revelation for me personally. Okay, I studied these things by heart. I know all these things mathematically. I knew all these things mathematically. Nobody told me really that the Heisenberg's uncertainty principle is not just for position and momentum of quantum particles. It is true in some form, some way, some shape, or some form for any pair of conjugate variables. Okay, what I mean is that if you are an electrical engineer and if you are talking about time and frequency, since they are conjugate variables, that same sort of principle applies there as well. That same sort of principle applies there as well. To tell you what I mean is that say we have a signal. We have a signal in the time domain. For example, let's say we have a signal in the time domain. Okay, and let's say the signal is in the time domain. The signal is something like this. Okay, a very precise signal. Okay, a precise sine wave. Okay, it's a precise sine wave, and this is, say, for example, sine omega t. So let's say sine omega t. Let's say sine omega naught t. Okay. So this is the representation of the signal in the time domain. Okay. Okay. Now, if I ask you this question, okay, in what time do I see the signal? I mean, where does it exist? Where does the signal exist in the time domain? Where in time? Where in the timeline does the signal exist? It exists everywhere. Okay, it exists everywhere. So you could think about any time, any moment in time, and this signal will be there. So, in other words, we can say this signal is imprecise in terms of time. What I mean is that this signal is everywhere if I am looking at it at different times. Okay. But if I calculate the frequency response of this, so essentially if I draw the Fourier transform of this, okay, we know what the Fourier transform of this one looks like. The Fourier transform of this one is extremely precise. So we have one impulse here, okay, and this has value of j pi, and this has the value of minus j pi, okay, and this is at omega 0, this is at minus omega 0, and this is in the frequency domain. Okay, this is the Fourier transform. So try to understand, this signal actually exists everywhere in time, but this signal exists only precisely in frequency. Okay, in the frequency domain we can see that this signal is extremely precise. If somebody asks you where in the frequency domain does this signal exist, we will say, okay, this signal in the frequency domain exists at omega 0, at frequency omega 0 and frequency minus omega 0, exactly at those points. But where in time does this signal exist? The answer would be everywhere in time this signal actually exists. Okay, so to give you a rough example once again, let's say I have a signal that exists everywhere in time. Say for example, the signal sort of looks like this. This signal exists everywhere in time. Or maybe just to give you a again better example, say this signal actually exists somewhere in time, but so then of course that signal decays. Okay, so the signal existed for some amount of time, and then the signal decayed. So if you had drawn the corresponding Fourier transform for this, so for this sort of signal, I could say, okay, let's take a very basic example. I would say, okay, let's take a very basic example that would be fine with us. Let's say we have a signal that is a pulse. Okay, that is a pulse, and that pulse is actually, say, okay, so that's a signal. Okay, so now this is not very imprecise in time, so we would say where does this signal exist in the time domain? So we would say from a time minus t0 to plus t0 in the time domain it actually exists, and beyond that it is 0. It is actually non-existent beyond that, in other terms. So this is less precise, sorry, this is more precise in the time domain. Okay, so we can precisely tell that, okay, if you visit the timeline, so this is the timeline. Okay, so if you visit the timeline from a time instance of minus t0 to a time instance of t0, then only you will get to see the signal. Otherwise you won't get to see the signal. So we more precisely know about the position of this signal, time domain existence of this signal. So in the conjugate plane, so in the frequency domain, if I draw the corresponding frequency response, okay, so this is magnitude, okay, just keep in mind. So if I draw the corresponding frequency response, so essentially mod h omega, so that would be a sinc function, and let me just draw the sinc function, modulus of the sinc function. So that would be, that's the frequency domain representation. So that's the Fourier transform of that pulse. Okay, so now since this is compared to this one, this is more precise in the frequency domain. Okay, so this was extremely imprecise, extremely not precise in the time domain, but it's in the frequency domain it was extremely precise. In the frequency domain it was extremely precise. So since this signal lasted for a very long time and like that, so this had only a particular set of frequencies. Okay, for this one, this signal was extremely imprecise. Extremely precise compared to this, very precise. It was so precise in the time domain that in the frequency domain, we see that the frequency response of this, or the frequency composition of this, is imprecise. Now, if I ask you, what are the frequency components in this signal, you will say, okay, all the frequencies components that are in between these frequencies, and they have varying magnitudes like that. So the frequency representation is now imprecise. Okay, the frequency representation is now imprecise. So let me ask you, what is the most precise signal in the time domain? The most precise signal in the time domain is, of course, the impulse. The impulse is the most precise signal in the time domain because it only exists once. So we could just happily say, only if you visit the timeline at t equal to 0, then only you'll get to see this signal. And this is our happy delta t impulse. Okay, if you only visit the timeline at t equal to 0, then only you'll get to see this signal. Otherwise, you would never see the signal. This is so precisely known in the time domain. So we precisely know its position, in other words. Okay, sort of. Okay, while it exists in the timeline. But what is its frequency then? Of course, we know that the frequency, essentially the Fourier transform of this, mod x omega is a constant, and that is there everywhere in the frequency. So in other words, if I have a signal that is extremely precise in terms of time, it would be extremely imprecise in terms of frequency. Okay, so in that sense, we can say that this signal has every possible frequency present in it, present in it. So this signal is only at a single instance in time. So this is extremely precise in terms of time, but this signal is everywhere in terms of frequency. So this is extremely imprecise in terms of frequency. Okay, so that is Heisenberg's uncertainty principle. And let me tell you, I can get rid of this entire picture, and I can instead say, okay, this is representing the position of a quantum particle, and this is representing the momentum of a quantum particle. The discussion would be just be the same. Okay, if this is the precision with which we know the position of a particle, then this is the precision with which we know the momentum of the particle. If this is the precision with which we know the position of a particle, we exactly know where the particle is. Okay, then this is the precision with which we know the momentum of the particle. In other words, if we exactly knew what position the particle was at, we won't know anything about the momentum, because we cannot really say what frequency component it has, just like that. So this discussion actually boils down to every set of conjugate variables that exist in nature. Okay, this is just one example. In diffraction, in the physics of diffraction of light, the same discussion actually applies to, once again, to a set of conjugate variables. So there are many situations where we apply this sort of integral transforms like Fourier transforms, etc., and we get to see there's conjugate variables. And these conjugate variables do tell us that if something is precisely measurable or precisely known in the time domain, it is very imprecisely known in the frequency domain. And if it is very precisely known in the time domain, for example, very imprecisely known in the time domain. So for example, what is the signal that is extremely imprecisely known in the time domain? Of course, that is the constant 1. Okay, so where does it exist in the timeline? Everywhere. What is the value? The same. So this is so imprecisely known. So this is like saying I exist, I am everywhere, I am always there, something like that. Okay, so this is so imprecisely known in time. Okay, but what is its frequency? So in the frequency component, this will be so extremely precise. Okay, so the frequency of this is just an impulse. So this only has one frequency. This only has one frequency, and that's just 2 pi delta omega. That's a big, long, boring, I hope, but useful discussion on some quantum principle in real life, really. But the thing is, you understand something, that these conjugate variables are so wonderful, really. Okay, they are so associated with each other like that, beautifully associated. Okay, and there is just another property. That actually is really useful and will be understood later on. That something. So if I draw the picture of something happening in the time domain as well as in the frequency domain, okay, there is a way of stating, okay, mathematically we are going to discuss this later on, something that happens first in the time domain will happen last in the frequency domain, and just like that, something that happens later on in the time domain happens earlier in the frequency domain. Okay, so if you draw something in the time domain and correspondingly if you draw the similar thing in the frequency domain correspondingly using Fourier transform or Laplace transform, you would see the features or the behaviors that appeared earlier in the time domain would actually have a similar effect in the frequency domain, but later on in the frequency domain, okay, at a later part of the frequency domain. And similarly, the things or the features that happened at a later time in the time domain would happen quite early in the frequency domain. Okay, so with that and understanding, we can actually we would actually develop a few methodology, and where we are going to describe some initial things that are happening in the time domain, and that would be telling us some final things that are going to happen in the frequency domain. Okay, and then we are going to learn some initial things that happen in the frequency domain, and that would give us information about what happens when a long time has passed in the time domain. Okay, so these are so wonderful things, really. And just to give you some overall understanding how I have a feeling of these subjects. Okay, you need to understand the mathematics as well as you need to have the feeling about these subjects, then only you understand the whole thing. Okay, as we were talking about, I don't think we will be able to finish stability today, but we are going to at least derive some part of that. Anyway, so we are talking about complex frequencies. So this sigma, as we were talking about, this sigma is composed of, sorry, this S is composed of sigma plus j omega. Okay. Now, of course, we this term appears on top of the exponential, right? So this term is not just there as it is; it appears on top of an exponential, right? So what is this term really actually telling you? What is this term really actually telling you? That's the question. If that is the question, then we have to look at this e to the power minus st. We have to look at this e to the power minus st, and that is actually getting multiplied with it, because that is the frequency representation of that signal. Now, if I represent this, so I have e to the power minus sigma plus j omega t, and that is obviously e to the power minus sigma t times e to the power minus j omega t. Again, if you have any query, please ask at this point. Remember, this sigma is a real number. Okay, so this e to the power minus sigma t is a real quantity, and then we have e to the power minus j omega t, and that's obviously cos omega t minus j sine omega t. We know that is a general complex representation of a sinusoid. So this is again a sinusoid. What is this representing? This is representing a general sinusoid of frequency omega radian per second. Okay, so this is showing you an oscillatory signal. So in other words, this is a general sinusoid of omega radian per second frequency. So by just knowing omega, you know the frequency of the sinusoid associated with this. But sometimes we cannot just be happy with that. What happens is that, what is the frequency once again? Frequency, this omega, tells you how frequently the signal changes, or how frequently the signal repeats itself. Okay, so if the signal has a frequency of 2 Hz, means it repeats twice every second. If the frequency is 10 Hz, it repeats 10 times every second. Okay, that is what omega tells you. But what does this sigma term tells you? This sigma term actually tells you something about the magnitude of this sinusoid. So just to tell you what I mean, let me just draw 2 pictures here. Once again, hold on. Let me just draw 2 signals, okay? And again, I try my best to actually get through to you. Okay, let's say I have 2 signals, and one of them looks like that. Let's make it okay. Fine. Assume that it's a sinusoid, okay, even though this does not look like one. Okay, that's a sinusoid, not a problem. I hope you can actually at least assume that it's a sinusoid. Fine. So that's t, and let's make it bigger. Okay, right. So that's a sinusoid. Now, of course, we can perfectly describe this sinusoid by saying that, okay, it has a frequency of this and that. Okay, so we can say that, okay, fine, this sinusoid has a frequency of omega radian per second, whatever omega is in this one. Okay, but that would actually describe the, what should I say, the repeating nature of this sinusoid. Okay, the repeating nature of this sinusoid. Okay, it's not a problem with us. Okay, so omega radian per second is the frequency. So for example, just to give you a concrete mathematical value here, let's say this is 1 second, this is 2 seconds, and this is like 0 second, something like that. So obviously this signal actually takes 1 second to repeat itself. So this signal is a periodic signal, I would say. This signal is a periodic signal with a period of 1 second. So this time period is 1 second, and the frequency correspondingly is 2 pi by t essentially. So that's 2 pi radian per second, or just 1 hertz. Okay, so frequency is 1 hertz or 2 pi radian per second. That's not a problem, right? That's not a problem. But what if something else as well happens to this signal? Say for example, I have a signal that kind of looks like this. Instead of being something like this, the signal gradually changes values. I am trying my best to draw this. Just hold on. I think I have to draw it Okay, so look at this red one. Okay, look at this red one. So if I ask you what is the frequency of this red one, yeah, that's a very good suggestion. Okay, why not use that instead? Yeah, perfect suggestion. Why not use that? Just hold on for a second. Huh? Let me launch Python here. Okay. Okay, and let me switch to another view. All right, so we have Python here. Okay, so let me plot these things. Let me just say p is equal to instance 0 comma 10 comma not a problem. Okay, and let's say x1 is a signal, and that would be just a sine of t, not a problem. Then again, let's say sine of t, not a problem. Fine. And same, I have another signal x2, which is xp times sine t. Okay, let's plot everything. So t comma x1, t comma x2. Okay, let's make this okay, bad drawing, bad drawing. Hold on. Let's make this 0.5. Okay, okay, you know what? Let me change the values here. I don't know how much you can see. I'm of course not teaching Python programming here. Okay, so even if you cannot see, I really doesn't matter really, because it's trying to show you what I mean. Okay, that would be fine, hopefully. Yeah, this is something I wanted to show you. For example, let me just put the grids. Okay, hold on. Okay, someone is saying why no numpy? Yeah. What happens is that in Spider you have a setting. That's a very good question. Those who are using programming here, learn a bit of Python. Okay, so if you go to settings and then in where is it? Hold on. I hardly ever touch this because these things are so perfectly configured. I configure everything so perfectly. Python interpreter. Okay, and not Python interpreter. I hope this is in IPython. Yeah, IPython console. Yeah, last one. So uh, here, yeah. So here in the IPython console settings, in the graphics settings, I say automatically load PyLab and NumPy modules. Okay, it's the PyLab and NumPy modules. So what happens is that whenever I launch Spider, okay, it is actually doing something like a percentage PyLab for me. Okay, that is something we actually, that's a magic command. Percentile PyLab is a magic command that we use in Google Colab as well as in Jupyter Notebook to import everything or rather most of the things from NumPy and Matplotlib. So that is actually happening by default because I have checked a certain checkbox in the settings. Okay, because of course I often use this for this sort of tasks. Okay, so this is a fantastic picture now. Very, really much better picture than this. Now, what I mean is that this signal, that omega t, that signal, this omega, sine omega t, this one, okay, this has a certain frequency. Okay, this has a certain frequency. In this one, this has a frequency of 1 radian per second. This has a frequency of 1 radian per second. Not a problem again. Okay, so this blue one has a frequency of 1 radian per second. Let me take a screenshot of this and put it on the actual diagram so that we actually can discuss what I'm trying to discuss here. Okay, better picture. Again, thank you for suggesting that I use a programming language instead. Of course, we know a lot of programming, so we can actually happily use that. Why not? All right, thank you. Anyway, so let's start once again. So we know this for this blue one, here the frequency is something like omega, and that omega is 1 radian per second. Okay, that's not a problem. We know the frequency of this signal. Now question is, what is the frequency of this orange one? What is the frequency of this orange one? And while we are at that, let's get rid of that. All right, so what is the frequency of this orange one? Can anybody tell me? The answer is we cannot say the frequency of this, even though somebody is saying the same, but the frequency inherently tells you that this signal repeats itself. Okay, so we are saying this signal has a frequency of 1 radian per second, which means after every 2 pi second this signal will repeat. So the blue one actually repeats itself. That's why it is a periodic signal. That's why we can talk about frequency. But this signal, as you can see, does not repeat itself. So this signal is aperiodic. The orange one is aperiodic. And how can we talk about frequency of an aperiodic signal? We can only talk about the frequency spectrum through Fourier transform, right? It has many frequencies. So what is the frequency of this aperiodic signal? None. It is aperiodic, right? It is aperiodic. Even though, notice very carefully that it is crossing the axis at exactly the same instances the other signal is crossing the axis. So let me just draw the axis, thicken the axis. So this is the time axis. Maybe it got a bit thicker. Yeah. That is the time axis. Okay, that is the time axis, and not a problem then. And this is the, of course, magnitude axis. Once again, okay, and these are the points. These are the points at which they cross the zero. Okay, zero. So as we can see, they appear to have a very similar frequency, or it is very similar nature. Okay, only thing that happened that this signal was decaying, that this orange one was decaying, right? Or could be increasing. So its magnitude was not the same, although the behavior is the same. So some people, some of you already inherently by default told me that okay, it has the same frequency. No, it has something similar to the frequency of this. You see, this has 1 radian per second in terms of its frequency, but this one is aperiodic by definition. This is not repeating. The orange one is not repeating, so it is aperiodic. We cannot talk about frequency, or can we? Yes, we actually can talk about the frequency of this signal, and we can say that this has something similar to a 1 radian per second frequency. But not just that, it also has a decaying factor associated with the frequency. That is making sure that signal is aperiodic. Okay, what is happening? Why can we not talk about the frequency of this signal? Because this signal, the orange one here, is aperiodic. Its magnitude is changing, right? Its magnitude is changing. And that's why we cannot just straight up say it has a frequency of this much omega. Omega is this much radian per second. We cannot say that. And that is why this omega, this concept of simply using omega as the frequency actually falls short. Here, if we just used omega to represent the frequency, we cannot represent this signal, unfortunately. We cannot represent this signal. Okay, because this signal, rather we cannot talk about the frequency of this signal, even though this frequency, omega 1 radian per second, is telling something very important about the signal. It is telling us that about every 2 pi second, the signal is crossing the same amount of zeros as this one. So crossing from positive to negative and negative to positive is called a zero crossing. It is telling us the behavior, the nature of this signal, how many ups and downs there are. Okay, the number of ups and downs in this signal are equal to the number of ups and downs in this signal as well. So this frequency term will actually tell you all these things. How many zero crossings are happening? When are the zero crossings happening? It is telling us all those. But still, we cannot say that this signal, this orange one, has 1 radian per second frequency. Yes, we cannot say that, unfortunately, because this signal, this orange one, is aperiodic. That's why we cannot say that this signal has this frequency, and that is where the classical convention for frequency falls short. We cannot just say frequency like that, because that only limits us to describing periodic signals. But often many vibrations, so this kind of oscillations come from vibrations, right? Many vibrations in real nature are damped vibrations, right? A damped vibration. If you make something oscillate in the air will resist its motion, and eventually the motion will die down. Okay, motion will die down. Okay, but the zero crossings are still going to happen at the same time. Okay, so you might already know, if you take a bigger pendulum or a smaller pendulum, okay, and whatever pendulum, and even if it dies down, even if the motion dies down, okay, due to air friction or whatever, okay, the zero crossing still happens at the same time. Okay, it still happens to cross the zero I mean, takes the same amount of time. Even though magnitude reduces, magnitude of the oscillation reduces, the zero crossing, okay, the total time rather, it takes up to go back and come back here, kind of is still the same. Okay, this is sort of a damped harmonic motion. Okay, harmonic motion, which is a repeating motion, but damped. Okay, something is dissipating the energy. So to describe this sort of motions, we use the complex notion of frequency. Okay. Now, in this complex notion of frequency, we can perfectly describe the frequency with an associated damping term. So this term is describing the damping term. So when we have that, now with that being said, if you noticed what I wrote in Python here, this was the signal. This was the signal. Okay. Oh, cannot see. Sorry. If you notice what I wrote in Python, this was the signal. So essentially, the signal that you have here, this orange one, this one was just this blue one was just sine t, and this orange one was write it down. This orange one was e to the power minus 0.2 t sine t. So because of this factor, we cannot say that this is a periodic signal. Okay, this is a periodic signal, but this sort of decaying or increasing signals are so common in nature that we introduced another term to describe the frequency. So what we say is that, okay, it's a sinusoid. It has a frequency of 1 radian per second. So this is part of a sinusoid. The orange one is part of a sinusoid. The inherent frequency is the oscillatory term in this has a frequency of 1 radian per second, but it also has a decay term, and that decay term is this much. Okay, decay term is this much. So it given by e to the power minus sigma t. So in this one, in this picture, we can say that this orange one is periodic if we consider the complex frequency. So this is complex. This is periodic in the complex frequency. What should I say? In the complex frequency consideration. So if we consider complex frequency, under that, this signal is periodic. The orange one. Let me repeat once again. You can quote me on this. This sort of signals that decay, okay, like this, exponentially decay, they can be considered periodic signals under complex frequency notion. If we consider frequency to be a complex quantity, then decaying or exponentially rising, exponentially decaying or exponentially rising signals can be considered periodic under the notion of complex frequency. So here we would say that this signal, okay, so if you again think about this as sigma plus j omega, this signal, we would say that this signal has a value of sigma which is equal to minus 0.2. There is just a small problem with this notation. Just keep in mind, we are going to explain that. So we actually not talk about minus st, we talk about st, because that is the standard notion of positive frequency, positive notion of frequency. Just keep in mind, we talk about this. Minus essentially talks about the rotation in the other direction. Okay, so we essentially have something like that. So as plus sign, so it's a positive frequency notion essentially. So we would say this sinusoid, this one, I mean this decaying sinusoid, the orange one, has a complex frequency represented like this, and 1. Okay, omega is 1. Both of them have the same unit. Keep in mind, because we are adding two terms, right? Sigma plus j omega. If omega has a unit of radian per second, this sigma also must have a unit of radian per second. They also have the same unit. So in other terms, we can just say for this one, we can say for the blue one, we can say it has a frequency of 1 radian per second. That's a real frequency. But for this orange signal, it has a frequency of minus 0.2 plus j1 radian per second. So this is a complex frequency. So this complex frequency is telling me that this signal is exponentially decaying. So this term, okay, that sigma term, okay, this is omega, okay, just like that. Okay, this omega is telling me as the repeating feature, and this is telling us how the signal is decaying or increasing in nature. So that's how, using complex frequency, using the notion of complex frequency, we can describe far more classes of signals, far too many classes of signals as periodic signals, even though they are not. Okay, in the conventional sense, the orange signal is not periodic because it is not repeating. Okay, but in the complex sense, in the sense of complex frequency, this is a periodic signal. Again, well, let me repeat. In the sense of complex frequency, this orange signal is a periodic signal. So let me write it down here. Okay, this is, so in the sense of complex frequency, yeah, it is periodic. So in the sense of real frequency, this is not periodic, but in the sense of complex frequency, this is periodic. That's why complex frequency is so important. Okay, in many natural phenomena are of course by default damped, and this damping can be described as some combination of exponential damping. Okay, some sort of exponential decay. Okay, for example, if you have a resistor and a capacitor connected in series, and the capacitor is charged, okay, the way the charge gets depleted is an exponential function, exponential decay. Okay, so just like that, so many natural decaying phenomena are exponential in nature. Okay, similarly many natural growth phenomena are also exponential in nature. For example, bacteria growing. Okay, bacteria growing. So if for example 1000 x number of bacteria enters my body, then, and if they can properly reproduce, then the next day there will be 2x number of bacteria, then the next day there will be 4x number of bacteria, and the next day there will be 8x number of bacteria. So they will exponentially grow. So that's a geometric growth. Okay, exactly. Decays also happen geometrically or exponentially. So that's the opposite way. Okay, so many natural phenomena are there that can be described with exponential growth or exponential decay. So the concept of complex frequency is really important to describe all that. I hope I got through to you with this idea. So complex frequency is inherent and so important in the concept of control systems, because so many natural phenomena, so many natural things that we try to describe here are decaying oscillations. Okay, can be described as decaying oscillations, and so the complex frequency is useful in this. Okay. So in any case, if you have questions, please ask right now before we proceed further with this. I believe you understood what I meant to describe here. Okay. Okay. So since you are saying all clear, you understood everything. When I studied this for the first time, I did not understand something very important. Okay. So it's a complex number, right? S is a complex number, and S is like sigma plus j omega. Of course, we understand what omega is telling us. Now, any complex number can also be a real number. Okay, yeah. So again, let me repeat. This orange signal is a periodic signal. Okay. If we think about in real terms, you would say, okay, this orange signal is a periodic signal multiplied with an exponential decaying factor. Okay, that is exactly what we did with Python. Okay, this orange signal was a periodic signal originally, but multiplied with an exponential decaying function. So in real frequency terminology, this orange signal is not periodic. It's an aperiodic signal. But in the complex frequency terminology, if we consider frequency to be complex numbers, then this orange one is a periodic signal. Let me once again repeat. Any signal, okay, that is periodic otherwise, but is decaying or increasing exponentially, can be described in terms of complex frequency, can be described as a periodic signal using the complex frequency notion. Okay, so I can say this signal, so this orange signal is a periodic signal. This signal is a periodic signal with this frequency. The frequency of this signal is -2 plus 1j radian per second. The frequency of this orange signal. The moment we say frequency, a particular frequency, singular term, frequency, we mean it's a periodic signal. It's repeating in the complex sense. So the complex frequency actually tells you that this is a periodic signal, but in the complex frequency understanding here. So if you consider frequencies to be complex numbers, you can describe this sort of signals that are otherwise going to be considered as aperiodic signals. And this is by virtue of Laplace transform, because see, with Fourier transform we cannot say that, because with Fourier transform we just have the frequency terminology. We don't have any other complex frequency terminology there. But for Laplace transform we can actually talk about complex frequencies, and this sort of things are really, really important. And that's why you might see that, okay, dogs are barking. So as I was saying, the complex frequency is, okay, that representation. Okay, so that's a complex number, right? S sigma plus j omega. My question is, what if it's a real number? Because real numbers are subset of complex numbers, right? We know real numbers are subset of complex numbers. Subset of complex numbers. Real numbers are subsets of complex numbers. Okay, so we know that. So with that understanding, what if we say under that complex understanding, the frequency AC is something like a -2 plus J0. I'm explicitly writing J0 to indicate that I'm using the complex notion of frequency. What if the frequency is something like that? Only this part is there, only the sigma part is there, and there is no omega part. Omega part is 0. What if something like that? What if, so my question is, what if the omega is equal to 0 and sigma is equal to non-zero? Sigma is not equal to 0. What if something like that is happening? What is the description then? How am I going to describe it? What kind of signal is it? Okay, that is also somehow a periodic signal, because as long as I can describe a frequency for that signal, that also qualifies as a periodic signal. So this signal that has a this sort of complex frequency where there is just a sigma, no omega, that's also a periodic signal, because now the signal would have a frequency representation of e to the power, once again, s, st, and there e to the power s would be like -0.2 plus j0 t, and obviously that's going to be e to the power -0.2 t. What is that? That's an exponential decay. That is representing an exponential decay. This is a pure exponential decay. Pure exponential decay. Okay, but that is also being considered as a periodic thing in the complex frequency notation. Okay, let me once again get back to Python and draw this. Let me just draw this. So let's say I have x3, and that would be just this pure exponential decay. Okay, let's say this is x3. Okay, once I do that, let's put that drawing in here. This t comma x3. I'm sorry, let me start it once more. All right, here, this green one, which is the exponentially decaying function. So this is a purely exponential decay. Okay, pure exponential decay. This thing is also a periodic signal if you consider the complex frequency. So in the complex frequency domain, in the complex frequency understanding, this is also periodic. Try to get the grasp of it. There are so many yes, in the complex, not in the complex plane, I mean in the complex frequency terminology, in the complex frequency understanding. Okay, so if you consider frequencies to be complex numbers, then all these things that you see on the screen are periodic. Things that are periodic in the real frequency terminology are also periodic in the complex frequency terminology. There is nothing confusing about that. But things that are aperiodic in the complex frequency in the real frequency terminology are or can also be considered to be periodic signals in the complex frequency terminology. So let me take the screenshot of this as well, and let me clear up the confusion a bit more, or maybe confuse you even further. I don't know. It's going to be either way. Okay, so all these things that you see on the screen, one of them you already know as a periodic thing, the blue one, right? But the other two you know so far, or you have known these two as aperiodic things. If you consider if your frequency is a real number, if your frequency is a real number, the green one and the orange one are aperiodic. Okay, they are not repeating each other. But if your frequency is a complex number, then this green one and the orange one, they are periodic. Yes, question is, how do you physically see it as periodic? You don't. This is just a mathematical representation. Okay, how do you see impedance as a complex number? You don't. This is just a mathematical representation, and this complex frequency, the real part of the complex frequency. Try to understand. This real part of the complex frequency is telling you how quickly or how slowly it is decaying, and this complex part of the complex frequency is actually telling you the repeating nature. Okay, repeating nature. So in other words, for this blue one, I could say that the complex frequency here it is the complex frequency here is 0 plus 1, 0 plus j1 radian per second. Okay, for this one, for this orange one, I could say that the complex frequency is, for this orange one, I could say the complex frequency is -2 plus j1 radian per second. Okay, and for this green one, I could say that the complex frequency is just -2 plus j0. Notice I'm writing j0 to indicate that I'm using the complex frequency notation, radian per second. Okay, so notice again, once again, this term is denoting the decay or the growth of the signal, and this term is denoting the repeating nature. Of course, this signal, the green one, does not have any repeating nature, so that part is aperiodic, or rather that part is constant, in other words. Okay, whatever, that part is not there, so this is only decaying, okay, or rising exponentially maybe. Okay, just like that. Okay, so that part, the real part, is shows us the decay or the growth, and this is showing us the repeating nature. So this is both decaying and as well as repeating, so it has both the terms. Okay, so this is only repeating, not decaying, so this has a 0 part for that. Okay, let me just show you another example before I end this discussion. Okay, let's consider x4, and for that I would actually use something like exponential, say for example minus, not minus, say for example 0.2 times t times sine t. Okay, and let me plot all that, clear this, plot all that, comma x4. It was a bad idea. Okay, I have to actually, okay, fine, bad ideas are still ideas nonetheless. Write down great, not great like that. All right, sorry. All right, now the other things are not really visible. Okay, other things are not really visible because what happens is that I have another signal present in this picture, and that is exponentially growing. Okay, so I have another signal that is actually exponentially growing. So what I have drawn here is this, e to the power plus 2t times sine t. Now this is once again crossing the 0 exactly where the other signals are crossing the 0 as well, but this is actually growing, exponentially growing. All right, this signal is exponentially growing. The thing is, this is also periodic in the complex convention. Okay, and for this, of course, the frequency is +2 plus 1j, +2 plus j1 radian per second. Okay, so sigma is +2 and omega is 1. Okay, so that is the complex representation here. So this is again a complex exponentially rising signal. So exponentially rising signal, exponentially decaying signals, all these things can be represented, considered as periodic signals in the complex consideration. So in complex frequency, they are all periodic. Okay, for real frequency, they are not. Make sure to understand this. As far as real frequencies are concerned, they are not periodic. Okay, for real frequencies, these things are all aperiodic. But for complex frequencies, they can be considered to be periodic. And there is a funny thing. The funny thing is that you understand Dirichlet conditions, you understand Fourier transform, so you know that there are many signals that can be represented as sinusoid. Then you studied Laplace transform, so you know even though they cannot be represented as sinusoid, so Fourier transform do not exist, we can still calculate the Laplace transform. So Laplace transform essentially multiplies the decaying factor and calculates the corresponding components in a way. Okay, so it actually opens up the Fourier transform for many different other signals, many other types of signals. So the point being, we have many signals, types of signals for which we have a Laplace transform at least. Okay, right? And with that understanding, we can say that there are many signals that cannot be represented as signals that are composed of sinusoids. Okay, sinusoids. For example, again, once again, let me repeat what I mean. Okay, for signals that can be calculated, that for which we can calculate a Fourier transform, are signals that can be represented as a sum of sinusoids. Okay, I give you a signal, you can calculate a Fourier transform, which means that signal can be expressed as a sum of sinusoids. Okay, different sine waves. Okay, but what are sinusoids? Sinusoids are periodic signals in the real frequency concept. Okay, right? But since there are many other signals for which the Fourier transform does not exist, but the Laplace transform does, which indicates that there are many other signals which cannot be expressed as pure sinusoids or expressed as a sum of pure sinusoids, but they can be expressed as a sum of exponentially decaying or rising sinusoids. Okay, so there are many signals which can be described as a sum of many exponentially decaying or increasing sinusoids. That is exactly what Laplace transform tells us. So Laplace transform extends the concept of frequency into the complex domain. Okay, and now the moment we have that, all these are periodic signals. Not only the pure sine wave and pure cosine wave are the periodic signals, also these exponentially decaying and rising waveforms are also periodic signals. So if we extend our concept of frequency to the complex domain, then there will be many other types of signals that can be described as a sum of this complex frequency sinusoids. Okay, this complex frequency sinusoids. So if we now collect, so for Fourier transform, in our collection we only had real frequency sinusoids that had real frequencies, and we wanted to describe signals as sum of real frequency sinusoids. Now in Laplace transform we now have in our collection we now have complex frequency sinusoids. So these are all complex frequency signals. Okay, these are all periodic signals in the complex frequency. So now so I will answer your question. So now we have a lot more signals in our collection, and we can describe a lot more signals as a sum of these sort of sinusoids. So in other terms, you can now understand that we can, for the most part, describe any signal as a periodic signal as long as it has a Laplace transform. Okay. Funny thing is, in the complex frequency domain, you can hardly ever find out anything that is aperiodic. Let me repeat what I said. In the complex frequency domain, you can hardly ever find out anything that is aperiodic. You can either represent it as a complex frequency, or you can actually represent it as the sum of many complex frequency sinusoids, complex frequency components. Okay, so the complex frequency extends the barrier so much, so that extends the area so much. In fact, okay, applicability so much that there is hardly anything that is aperiodic. Everything is periodic. So there is a common, although it's a very misnomer, there are things that are still aperiodic. Okay, but there are hardly anything, I would say. There are hardly anything that is aperiodic in the complex consideration. Okay, you can either consider it as a complex frequency, write it down as a complex frequency, or you can write it as a sum of complex frequency waveforms. Okay, so Laplace transform actually does that. So now you understand, I believe, where Laplace transform is a greater thing, as a more generalization of Fourier transform. If Fourier transform did this much, Laplace transform did infinitely more. Okay, because it has infinitely more different types collections of frequencies. So now if somebody asks you what is complex frequency, you can give them a 1 hour lecture or 2 hour lecture, right? What complex frequency is. Right? So I hope this cleared up your confusion. See, let me be very honest. You won't find any control system lecture, or you won't you ask your classmates in other batchmates, in other universities and colleges. I can assure you, even at premier institutes in India, they won't teach you these things. Okay, because in some understanding, knowing these things is not essential. Because some people think, or rather some teachers think, that knowing these things is not essential. Rather, let's complete the syllabus. Okay, so S is complex frequency, done. Okay, forget about it. So I'm taking a full class and describing all these things so that you have a feeling of how these things really work. Okay, so in my honest opinion, if you don't have the feeling about the subject, you cannot really do anything good with this. Okay, now let's go back to the question at hand. So one of you asking, is this because in complex frequency we are considering conjugate pair? No, not really. S is not because S is a conjugate variable to T. S is not complex because it's a conjugate variable to T. Let me once again, let me go back. See, this omega is once again a conjugate. Say that's a Fourier transform. Okay, omega is the conjugate variable to t. Okay, omega is the conjugate variable to t, so it has a reciprocal unit of t. Okay, just like that, sigma is also a conjugate variable to t. So sigma itself is also a conjugate variable to t because of the same understanding here, right? So sigma is also a conjugate variable. So both sigma and omega, they are conjugate variables, and this s itself is a conjugate variable because it is a sum of two conjugate variables. It is a sum of sigma, which is a conjugate variable. It is a sum of j omega, sigma and j omega. J omega is also a conjugate variable if omega is a conjugate variable. So both of them individually, sigma and omega, are conjugate variables to t. Okay, with respect to t, both sigma and omega, they are conjugate variables. And since s is a sum of those two, this is also a conjugate variable, but not in the straight way you might think. Okay, not in the straight way you might think. S is a conjugate variable because it is a sum of two conjugate variables. Sigma is a conjugate variable, omega is a conjugate variable. Both of them have the same unit, radian per second. Okay, and they mean different things, but they are conjugate variables. And since s is a sum of those two conjugate variables, the sum is also a conjugate variable. That's how s is a conjugate variable. Okay, so you now understand these things, right? So maybe when you were little children in maybe in our basic school, when we studied algebra or we started solving equations for the first time, if somebody gave me an equation like x square plus 1 equal to 0, it is not solvable if we only consider real numbers, right? There is no real solution of this. But in complex number, we have solutions, two solutions in fact for this, right? So the moment we extended our concept of numbers, so real numbers are essentially a line, just a line, but complex number is not in two, so it's a plane, it's a whole plane, so it's way more. Okay, there are way more complex numbers than there are real numbers, right? The understanding is like that. So the moment we extended our idea to complex numbers, we can solve any other equation, any equation like that. Okay, so any nth order equation would now have n number of solutions, if not in the real plane, but in the complex plane. So that's the idea here. So the moment we extend our boundary to complex numbers, understanding to complex numbers, we open up lots of possibilities. So if we consider frequencies to be positive, so real numbers, then we only have this much to discuss. But if we describe frequencies as complex numbers, then we have a lot more to discuss. There are a lot more things we can handle easily. Okay, there are a lot more things we can consider to be periodic with the notion of complex frequency. So that ends our discussion on complex frequency. I'm sorry to say that we couldn't have any discussion on stability, so let me get rid of that. Okay. Okay. Now, just last thing we need to discuss is the S plane. What is S plane? S plane is the complex plane. Okay. So essentially, is x since S is a complex number, just like we studied in your school level, so that if Z is a complex number represented as x plus iy, rather x plus jy, it is just the coordinate plane like that. And here I have the x abscissa and the ordinate. It is just the coordinate plane. That is something we call the Z plane in the complex notation. Just like that, we have S, which is equal to sigma plus j omega, and we can actually construct a plane on that. And here that will be the abscissa, and this will be the ordinate. Okay, so rather the omega axis, let's say jy. Okay, and that is going to be considered the S plane. So this is very similar to the complex plane that we are all familiar with. So that's called the S plane. There are so many things to discuss about the S plane. We are going to get to know those things in the future. But for today, try to understand that idea of complex frequency here. Okay, idea of complex frequency. Just to give you one last example, I need to draw that and show it in the picture because that will be really important in the future. Okay, let's put a grid. Okay, I want to mention this picture. Okay, so this was an exponentially growing signals. Oh, you cannot see. Sorry, this is an exponentially growing signal. So let me take a screenshot once again. Let me tell you that this is once again a periodic signal in the complex understanding. So this blue one that is hardly visible properly is a signal that has the complex frequency of that are the real frequency. So it's a periodic in real frequency consideration, and the real frequency is of course 1 radian per second here in this example. So the complex frequency in this one is 0 plus j1 radian per second. So this is periodic with this period, and this signal, the orange one, is also periodic. Now its frequency is plus 0.2 plus j1 radian per second. Okay, all right, so that is something you have to remember. So exponential decay and exponential growth can both be considered. So please, I would ask you to notice something we are going to discuss later on. Notice that if it is decaying, then the real part of the complex frequency is negative. The real part of the complex frequency is negative if it is decaying. If it is not decaying, okay, like this pure one, okay, pure sinusoid one, then the real part of the complex frequency is 0. And if it is instead of decaying, if it is increasing, then the real part of the complex frequency is positive. Okay, so again, that's the big picture we discussed today. So we have S, and that's sigma plus j omega. So this omega is the real frequency representing the repeating nature. Omega would be 0 if there are no oscillatory feature present. Instead of saying repeating feature, I would say oscillatory feature. Oscillatory feature. Okay, so omega would be 0 if there are no oscillatory features. For this green one, you see omega is 0 because there is no oscillatory feature in this one. If there are oscillatory features, then omega will be non-zero. Okay, so that's the real frequency, and this is not the real frequency. What I mean, this is frequency representing the oscillatory nature, and this is frequency, this frequency, okay, representing the damping, rather exponential damping, exponential damping or exponential growth. Exponential growth, and sigma equal to 0 indicates, means no damping, no growth. Neither grows nor gets damped. Okay, sigma greater than 0 indicates exponential growth, and sigma less than 0 indicates exponential decay. Okay, all right, so sigma equal to 0 means no damping, no growth, and that also indicates that it's a pure sinusoid, only oscillation. No damping, no growth, only oscillation. Oscillation if omega is non-zero at the same time. Okay, so we saw all the examples. Here we see sigma, so here we see sigma is a positive quantity, so exponential growth here. Okay, and if this is 0 here, then that will be just an exponentially rising signal. Okay, and just like that. So we have discussed all of that. So this S is the grandfather of all the complex frequency. Okay, all right. Any confusion with this? So if you have any query, feel free to ask. Otherwise, we are going to end the discussion here. I hope you understood something about the complex frequency. You have grown some feelings about the complex frequency, and that's really essential in my opinion. in my honest opinion, whatever you learn it properly, learn all of it. Okay. So there is a popular saying which goes, and who is an expert? So the definition of an expert is as a person who knows everything about something and something about everything. Okay. But rather I would tell you that instead of learning something about everything, try to learn everything about something. That's how I roll. Okay. I try to learn everything about something, not just something about everything. Okay. That would make you a jack of all trades, but master of nothing. So there may be a higher dimension. Yes, absolutely. Yes. Oh, so you definitely your brain works in 4 dimensions or 5 dimensions. I don't know, but your obviously your reasoning is perfect. We can actually describe frequencies using n possible dimensions. Okay, there are you can describe frequencies in n possible dimensions. That is not something we need as real physical human beings. Those who study quantum mechanics, especially something called string theory. I mean, what is this existence really? How to mathematically describe the fact that we exist even? Okay, so that is something studied in string theory, the subject called string theory in quantum mechanics. Those people do describe these things. Okay, for them, time is an n-dimensional quantity. Frequency is such a stupid number of dimensional quantities. I don't know. Okay, there are so many dimensions, like 27 dimensions. I don't know. Okay, so yeah. Okay, so those things. Maybe those things are all false. Maybe those things are all true. This is just theoretical physics. But yes, actually we can extend all this idea to multiple dimensions. Yes, really. But we don't need to, at least for this class, thankfully. Anyway, so that's the end of today's discussion. I hope you enjoyed it to some extent. I don't know. Maybe otherwise I bored you. In any case, I will see you in our laboratory class tomorrow. Thank you very much for being here. All right. So bye bye for now.